This video will introduce you to the normal distribution. The normal distribution is going to play a really important role in everything we do. Basically, the normal distribution allows you to take any type of data in any format and standardize it, all centered around how far each data value is from the mean. So essentially, it could transform numerous sets of data, which are all in different quantities. Some data might be in decimals, and some might be in the thousands, some might be in the hundreds. Gather a mean and put them all on a single normal curve. When we do put everything on our normal curve, it standardizes everything. Your mean, essentially, so if you have a set of data, suppose we have a mean of, I don't know, 120, I'm making it up. And then most of the data falls between 100 and 140. You might have a couple stragglers. The majority is around that mean. Let's suppose that's our X bar. So your data, if it's normally distributed, it kind of fits that bell-shaped pattern. If you were to make a histogram, your histogram would look like that. And what that means is, it's normally distributed. The majority will fall around so many standard deviations. And then think back to the empirical rule, 68% of the data will be within one standard deviation. So maybe one standard deviation comes out to here on either side. So you've got, 68% of the data there. Then you've got within 2 standard deviations, and within 3 standard deviations, you have the majority of your data. Now, all standardizing does is resets the data to a mean of 0. So it takes the 120 and centers that at 0, and then each data value gets standardized just like we did back in chapter 3 using a z-score for our normal distribution. It was x bar minus mu over the standard deviation. So basically, it turns each data value into how far away it is from the standard deviation. So again, all your values that are within 1, and then 2, and then you have the majority within 3. Okay, and then it just refits your data into these standardized values. What this will allow us to do, as you will see in this unit, is actually determine areas, because not all of our, suppose we wanted a data value that was somewhere around here at negative 1.5, and we wanted to know what percent of the data falls above 1.5 standard deviations below the mean. There's different things we might need to know. We can now use, once it's standardized, we have a nice table we can use, and we can figure out what that area. But before we get to that point, let's learn a little bit more about our normal distribution. So normal distributions, when they're not standardized, of course, can be very wide, like this one, if it has a very large standard deviation. It could be very narrow, like the red one, if it has a very small standard deviation. So let's take a look at an unstandardized set of data. So we've got a basic frequency table. It has a lot, this was an incredibly large data set, so we were allowed to have a lot of classes. We were just for our frequency. And basically it's just telling you how many data values fall within each of these classes. So you can see the numbers there of how many data values fall within each of the class. And then there's your histogram. So here's a large data set. We were able to do a lot of classes, which is unusual. Usually we just stick with about 5 to 7 classes, but in this one we have a large number. And your mean is going to fall probably, somewhere in the middle there. Your mean is going to fall, oops, sorry about that, somewhere here, about 64 point something. So there it is, 64.4. And you have a standard deviation of 2.4. So that's an unstandardized. And that's what you've been working with. And that's what you were working with back in Unit 2, when you were doing frequency tables. But as I said, everyone has a slightly different shape depending on how large that standard deviation is. But here's the deal. If you take any data set, no matter how large the standard deviation, no matter where the mean is, and you actually standardize the data. So take a look at what's done here. So if my mean was 9, my standard deviation is 2, I would take each x value in this data set and standardize it using this formula. I would do the same thing for the red value, but this time my mean is 3, my population mean is 3, and my standard deviation is 0.5. Okay, and there's the formula for that one. If I standardize all 3 of them, you will get the exact same graph. Because they are normally distributed, all of these would look exactly like this blue one. So this is why we standardize. It then allows us to look at a standardized table to determine areas. So for example, I wanted to know, my mean is now at 0. We're going to, again, talk a little bit more about this, but you can go to your table and look up 0. Let me just find my table. Hold on. So here's my standard. Notice 0 falls directly in the middle. You should have this printed. It is in your Canvas course information module at the top of your Canvas page. Please have this printed. You need to be able to use this table. And if you take a look, when you're at 0, notice 0.0, this area is 0.5, which makes sense because this table will always give you the area to the left here. And notice that for even negative 0.0, it's 0.5. Sorry. There it is. Sorry about that. So that kind of leads us to some of the properties. So I want to go down for a minute and look at some of the properties of our normal curve. Number 1, and most important, your normal curve, I want you to think of it as this way. Remember when we talked about probability and we looked at what's the probability, what is, if you were to sum up every possible probability of a probability distribution, you would get 1. All those probabilities would add up to 1. This is what you did at the beginning of chapter 5. So yes, this is the most important piece. The total area under your standard normal curve is 1. Okay, so if you look at it, so basically how you're going to use that is quite simply, 0's in the middle. Suppose this is the z-score of 1.20. And if I know that 1.20 has an area to the left of 0.8849, and I got that just by looking at my table. I looked up 1.20. All right, your table is always going to give you that area to the left of 0.8849. Knowing that it has a total area of 1, if I wanted the area to the right, all I would have to do is 1 minus 0.8849. And you would simply need to subtract and you would then get, I believe, 0.1151. Okay, one of the things I'm going to point out, one of the things I expect to see on your test, whenever you are working with normal curves, draw pictures. It helps you from having to think about which side or which area do I need for this problem. It also stops you from having to think, do I have to subtract from one? Don't I have to subtract from one? If you draw pictures, it makes sense. Because at 1.20 is to the right of 0. So obviously it's going to have a smaller area to the right than it does to the left. These are the kind of things that can help you catch mistakes. I expect to see normal curves drawn all the time. All right, some other things. Of course, it is completely symmetric around 0. We talked about that because at 0, it is exactly has an area of 0.5 on either side. It extends infinitely in both directions. So while we like to say most of the values are between almost 100% or between 3 and -3, once it's standardized, you will get scattered and there are probabilities of getting values outside of that. It does extend indefinitely. Okay, but again, most will fall between -3 and 3. All right, so we're going to start using this normal curve. I have your table in front of you printed out. This is a good time to stop the video and get it printed in front of you. You should always have that when you're working on pretty much anything from now to the rest of the end of this course. So I'm going to start to give out some z-scores, some z-values. So we'll start with z equals -0.21. For b, I'll do z equals 1.37. And then for c, I want to do in between both. Okay, so the first thing I said was draw a picture. Always, always, always. You're going to see me draw pictures. Remember, 0's in the middle. So you think about where is -0.21? Well, it's slightly to the left of 0. I'm going to draw a line. And for A, I want the area to the left. That means, and then I'm going to shade in the area I want. I want the area to the left of -0.21. All right, so you go to your table. Well, here's the good news. Your table always gives area to left only. So since our table already gives that, all we need to do is look up that -0.021. Your z-scores are in these two columns. Here's your negative and here's your positive z-scores. Your second decimal places are across the top for each of them. Okay, and if you have a z-score that's 3 decimal places, just round it. And all the numbers inside are your areas. So I'm going to zoom this in a little bit. No, I'm not. Doesn't want to work. That's okay. You have your table in front of you, so you should be able to see this with no problem. Do not just try to look off the screen. So -0.21. So that's 0.20. 0.21 looks to be 0.4168. 0.4168. That is the area to the left. Okay, look at your graph now. Well, it's a little under 0.5. And if you look at where your z-score is, it should be a little under 0.5 because 0.5 would be directly at 0. So again, we draw pictures to make sure our values make sense. Now for the next one, I want the area to the right. Okay, B, to the right of the specified z-score. So again, draw another picture. You are going to get tired of drawing the normal curve, but don't worry, it'll happen naturally, and it'll help you not only in this chapter, but throughout all of chapters 7, 8, and 9, and also if you're moving on to Stat 2. So now I'm going to go to 1.37, which is going to be a little more out here. I didn't draw the best normal curve, that's okay. But now I want the area to the right. So if I look up 1.37 on my table, there we go, 1.37, so there's 1.30, let me highlight it so y'all can see it. 1.37 is all the way down here. So it appears to be 0.9147. And now you think, wow, that area cannot be 0.9, right? Because your table gives you the area to the left only. So again, 1.37 was 0.9147. That's over here. But we want the area to the right. So you subtract from 1. We know the whole thing is 1. And then you can go ahead and put 0.0853. Makes more sense. That's going to be a small area. It's a small portion of your normal curve, so it's going to be a much smaller area. Now, you don't have a calculator, or you really want to truly understand the concept of symmetry. If on your table you looked up negative 1.37, which I know is not the number we're using, but I'm going to show you a little trick here. There it is. 0.0853. And again, that is due to symmetry. The idea behind that is simple. If I have 1.37 here, and I have a negative 1.37 here, this area, because remember 0 is perfectly in the middle, and its symmetric curve is equal to that area. So if I know negative 1.37 to the left is 0.0853, oh, that's the same as the positive to the right, 0.08. Okay, again, it's the same as taking the 0.9147 and subtracting by 1. But you really need to get a full understanding of how the normal curve works. Now, for part C, I want to go in between two values. All right, sorry, normal curves are sloppy. 0 being in the middle, 1.37 is out here, and negative point. I literally want just this area, okay? So I'm going to break this up a little bit so you have a good idea of why we are doing what we're doing. And I'm going to draw them each separately for a second. On the same, so there's 0. Okay, so I have 0.13 here. I would have this entire area for 1.37, and then I'd have negative 0.021, this area. And I want you to just stop for 1 minute and think about those two areas. I'm going to even get those two areas. We do have them. We know what they are. This one was, if you look up positive 1.37, and go to the left, this was the 0.9147. And of course, 0.021 to the left was a little under 0.5 at point. And before I tell you, I want you to think about how can I use that information to get what is in between the two of them. So did you figure it out? You have to subtract the two areas. You've got to take the area here, which was 0.9147, and subtract that area of 0.4168. Go ahead and subtract those real quick. Sorry, I didn't have it done ahead of time. 0.4979. That means just this area right here is 0.4979. Okay, so you're going to have a lot of examples in Math Lab, if you haven't done it already, to really help you understand how to find these particular areas. All right, and there's, of course, your normal curve. So we've kind of gone through all of these already. I'm going to move along here. Now, the next thing I want to do is to find a z-score. If you're asked to find the z-score having a specified area, well, that's a little bit different now. Let's suppose my area to the left is 0.0721. Okay, and I want to know what's the z-score that has that area to the left. I'm still going to draw a picture. Okay, and then I think about it. All right, an area to the left of 0.07. That's a small area, so you need to stop and think about where approximately is the z-score going to be. I'm going to start at the left because it's an area to the left, and 0.07 is really small compared to if the whole curve is a 1, 0.07 is only going to be a little bit, and I'm going to estimate it in my picture. I know the area, 0.0721. Now, it's an area to the left, so that's a good thing. I'm going to go to my table now. Now things are a little bit different. Let me erase what I was doing before so it's not messy. I now have to find in here. Don't get confused. We are not looking up 0.07 z-scores. It's not a z-score. I got to find 0.07. So I start looking at all my areas. They go in order. They start at 0. All right. Keep looking. Keep looking. I'm at 0.02, 0.05. There it is. 0.0721. And then I need to know, hey, what z-score is that? Well, it's negative 1.46. Negative 1.46. So then I go here and I say, oh, it's negative 1.46. So z 46. All right. Let's suppose I wanted a z-score. Let's do another one. With area to the right of 0.1579. Okay. Again, draw a picture, please. If you try to do this without drawing pictures, if you're getting them wrong on the test and I don't even see pictures in your work, you're not even trying. That tells me you just didn't even look at any of the work or the videos or anything. All right, area to the right. Okay, so now I got to start at the right. Well, it's definitely under 0.5. So I'll put it somewhere about here. I don't know where, but it's definitely under 0.5. 0.1579. Here's the problem though. Your table only gives areas to the left. So that's great. 0.1572, 0.1579. I need this area though. How do I get that? I go 1 minus 0.1579. Do that real quick. 0.1579. And I get 0.8421. This is the area I have to look up. And that will then give me this number, 0.8421. All right, so go to my page. Well, these are too small. 0.8421. 0.8421. All right, so here's the deal. You're not going to get an exact number. It's okay, we can estimate. All right, 0.84. Oh, that's 0.8389. That's 8413. And I want it, let me double check again, 0.8421. Ah, it's between these two numbers. All right, so here's what you want to check. Is it direct? So here's my question to you. Is it directly in between those two numbers, or is it closer to one of them? Is that 1 at the end closer to the 13 or the 38? Think about it. Okay, so 21 is going to be closer to 8413 because it's only what? 8.0008 away from here, but it's 0.00 like 21 would be 0.0017 from here. So it's closer. If it were directly in between, you could actually put a third decimal value of a 5. But since it's closer here, we're just going to use 1.00 for our value. Okay, your z equals 1.00. All right, so you have to understand how to look for the area and how to look for a z-score itself. So there is some special notation that you'll start to see later on in the course. If I have a z of 0.025, and this is just a special notation that means find the z-score with an area of 0.025 to the right. Sorry about that. Okay, that is a special notation for to the right. So in other words, I want to know what z-score has an area 0.025. Well, remember that's to the right, but your table gives you everything to the left. So you have to subtract, and it's 0.9750 here because it's 1 minus 0.025. So you're really looking up 0.975. Sorry, I wrote that backwards. 9750. So you're really looking up 0.9750. That's going to be way down there. So 978. There it is. 0.9750 is 1.9. That should be a 6. Yep, 1.96. This is going to be a very common one that we're going to use later in chapters 8 and 9, by the way. And also 0.05 is another very common one. And we'll go over those later in the course, the common ones. So this one now has an area of 0.05. So I want you to think about this a little bit. Keeping in mind, remember 0 in the middle. This one with an area of 0.025 was 1.960. Do you think this z value is smaller or bigger than that one? This is the type of stuff I want you to be thinking about so you truly understand how this normal curve works. So you think about that. Why we look up 1 minus 0.05. Go to your formula sheet. Now I'm going to look up 0.950. All right, so 0.950 is going to be directly, take a look at these two particular numbers. 0.950. So each of them is 5 points, 0.0005 points away. So it actually is going to fall directly in the center of the two of them. Because if I add 0.0005 to this one and subtract from that, I get like 0.950. So that means your value is directly between 1.64 and 1.65. So 1.64 and 1.65. And if you're not sure how to tell what's directly in between two numbers, you can always add them up and divide by 2. So what is directly in between them? 1.645. So this is going to be 1.645. So yeah, of course, it's smaller. It's closer to 0 because it has a larger area to the right. Okay? Okay, so how can we work with these and bring them into use them in an actual problem? So another thing I want you to kind of go back to and keep in mind is the idea of that empirical rule where, you know, about 68.26% of all possible observations lie within 1 standard deviation. About 95.44 lie within 2, and about 99.74 lie within 3 standard deviations. This is something also to keep in the back of your mind, but it is not exact. All right. So this is, again, these are rules that we've kind of talked about before. So now let's take a look at a problem. We're going to do a very simple problem that deals with IQ test scores. The Stanford Revision of the Binet-Simon Intelligence Scales are normally distributed. It has a mean of 100 and a standard deviation of 16. So again, we're always drawing pictures, right? What does that mean? It's normally distributed at 100. Right? And it has a standard deviation of 16. So what does that mean exactly? Well, if I were to go 1 standard deviation out, I'd be at 116. If I go 1 standard deviation in that direction, well, I'd have to do 100 minus 16. So that would get me what, at 84. Okay. 2 standard deviations is adding another 16 to that. That's 132. 84 minus 16. That brings me on the other side down to 68. Okay. And then 132 plus that 3rd standard deviation of 16 brings you to 148. And 68 minus 16 brings me down to 52. Okay, so this is my unstandardized normal curve with the actual numbers, how many standard deviations. When I standardize it, well, it just looks like this, right? With 0 in the middle, and you go 1, 2, 3, negative 1, 2, 3. What I want to know is what is the percentage of people that have IQs between 115 and 140? Well, in my unstandardized, 115 is going to be just shy of 1 standard deviation, right? That's 115. And 140 is going to be between my second and third standard deviation. So I want all of the area here between those two. Well, I can't look up 115 or 140 on my normal curve. What I need to do is standardize each of those variables. So I need to standardize the 115 and the 140. And I'm going to put them on my standardized curve. So this is my standardized curve. And I'm going to put them over here. Well, to do that, I need my formula. We did this back in chapter 3. If you go to your formula sheet, look at chapter 6. There is one small little formula. Z equals x bar minus mu over standard deviation. So let's do the 115 first. Sorry, not x bar. I apologize. I'm jumping ahead. It's just x. All right, so I'm going to use my x value of 115. It has normally the mean of 100. So my mu is 100. And my standard deviation is 16. So use your calculator real quick and get that value. I get 0.875. All right, so I want you to go back to remembering what we talked about. We said 115 should fall shy of 1 whole standard deviation, and it does. 115 is at 0.875. All right. So now let's look at the other one, which should fall between 2 and 3. Let's try it. That's 140 now. Same thing, use the same mu, use the same standard deviation. And again, it should be between 2 and 3. Let's double check that. Yep, 2.5. That makes sense because doesn't 140 fall directly between 132 and 148? Directly between the second and third standard deviation. And that puts us at 2.5. I'm going to just redraw this curve real quick because I don't like it. It's a little better. So again, zero's in the middle, 0.875, and this one's way out there, 2.5. All right, so now I want the area in between those two z values. You've standardized everything because we're now working with a real problem. Now you can go back to your normal curve, and first let's find the area to the left of 2.5. Okay, go to my table. 2.5 is down here. 2.50 is 0.9938. Now I need the area to the left of 0.875. 0.875. Okay, so 0.875 is directly between 0.87 and 0.88. It's actually exactly in between them. If it's exactly in between them, you're going to go directly in between these two areas. But if it falls closer to one or the other, you would actually just round it. But since it's exactly there, I'm going to go take these two areas, 0.8078, and I'm going to figure out what is directly in between them. You can probably look at it and see. So to do that, I'm just going to take 0.8078, add it to 0.8106, divide by 2, and I get 0.8092. 0.8092. Again, it's okay if it falls a little closer to 1. You can go ahead and just use the one it rounds to. But since it is directly in between, I'm going to try to get as accurate a number as possible, and I'm going to use 0.8092. All right, so to find the area in between, I must subtract these two numbers. Go ahead and do that. And I get 0.1846. So this area is 0.1846. All right, now I want you to go back to the problem and remember what was being asked. Determine the percentage of people. So take 0.1846, turn it into a percent, finish the problem by saying, hey, I understood what I was doing, and I now know that 18.46 have an IQ between 115 and 140. All right. So I also want to go through one problem where we have to standardize and go in the other direction, and then we're almost done with this. This is the last problem we're going to do on this particular video for Chapter 6. Well, no, there's one more thing. I'll talk briefly about normality curves. All right, IQ scores. So now, same test, same mean, same standard deviation. I want to obtain and interpret a 90th percentile for IQs. You might have remembered taking standardized tests back in grade school and high school and middle school, and they said, hey, you scored better than 76% of all the people that took this test, or you scored better than, and that's kind of what we're doing right now. What score would I need to get to my 90th percentile? So to do a 90th percentile, well, that means 90% of my data is underneath. So 90th percentile is going to be, 0 is a 50th percentile, right? Doesn't that make sense? Because 50% is below it and 50% is above it. So I want to go out to figure out what is the z-score that has an area of 0.90 to the left. Well, I need to get that z-score. So I got to look up 0.90 to the left. So I can go to my formula sheet. 0.90. Let's get rid of some of this other stuff. 0.90, okay? Remember, we're looking at areas. We are not, and this is what you need to remember. A 90th percentile is an area. It is not a score. So you can't use the z-score. That's an area of 0.90 you're looking for. All right, here we are. This one is 0.899. So this is only 0.0003 away. where this one is 0.0015 away. This one is way closer to 0.90. So I'm going to use that, and it's going to be 1.28. Okay, but that's a z-score. Okay, that doesn't give me any information about what that person needed to score to be in the 90th percentile. It doesn't give me any information about what you scored on the test. So now let's go back to our formula. Z equals x minus mu. All right. I have a z-score here. That's this value. I don't know what the x corresponding value is. I do know the mean is 100. And I do know the standard deviation is 16. You will also see on your formula sheet for chapter 6, the publishers were nice enough to go ahead and rearrange this formula for you and solve for x. And it looks like this. Okay, it does not matter if you plug it into here. And then we would have what? 100 plus 1.28 times 16. And this formula makes sense because you're starting at your mean and you're adding 1.28 standard deviations. Because remember, that's what a z-score is. It tells you how many standard deviations that a particular score is from the mean. And we want to find that particular score. So again, it doesn't matter which of these you solve. If you don't want to use this formula, you could just continue to use that one. Either way, go ahead and figure it out. And you get about 120.5. Approximately. I'm going to approximate that. Okay, so if you're in the 90th percentile, what does that mean? That means you are scoring about 120, at least 120 on this test. All right, you're scoring 120 on the test. All right, the last thing I just want to talk about very briefly, so briefly that yes, you will do a problem in Stat Lab, in Math Lab, but I'm not going to test you necessarily. You're not going to have to, let me put it this way. You might have to interpret a normality plot, but that's about it. What a normality plot does, it's kind of like, in order to use our normal distribution, we have to know that our data is actually normally distributed. Now, one way to do that is to do your frequency table and do a histogram and look at your histogram. If your histogram is in the shape of a normal distribution, as the one at the beginning in chapter 6 was, you can go ahead and assume it's normal and go ahead and use all the rules and the stuff we just worked on. The other idea is to do what we call a normality plot. And how a normality plot works is it takes a set of data. So this is adjusted gross income, and it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data values. And for this one, you actually have to go to your textbook, which is why I'm not going to make you make a normality plot on the graph because the data values are a bit hard to find. But in your textbook, in the appendix, and you can get this online, you can get all your appendices for your textbook. It is in Appendix A under Statistical Tables, and it is Table 3. So it is Appendix A, Table 3. And what it does, it'll do it up to, I think 22 data values. So it'll do it a data set up to 22 for your textbook, I think. Or I think it goes even further. No, it goes up to 30. It'll do a data set up to 30 numbers. So here we had, again, I think this was like 13. Let me see. Yeah, or 12. Was this 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So what you would do is look at Appendix A, Table 3, and you would go across the top of your table to the 12, and it would tell you what the normal score should be for all 12 data values. And it starts at -1.64, -1.11, and you would just list those values from the table. So this is from a table. And again, it's saying this, hey, if you had 13 data values and your data was normally distributed, these are the exact standardized scores each data value should be. So in other words, you take all your data values and write them in order. You position them. The lowest is first, and the highest is last. And the lowest data value, if it's normally distributed and you standardize your data, should be -1.64. The second one should be -111, and go on and on and on and on. And then what you're going to do is simply graph these numbers. So you graph the income across the bottom and your normal scores across the y-axis. So in other words, 7.8 gets a -1.64. So 7.8, -1.64, there's your first data value. And you make a graph. And what you're really looking for is a straight a line as you can get. So what do I mean by as straight a line as you can get? You really want it more like this. If it's following a relatively straight line, we would say yes, they have a nice normal distribution. Look at this particular data though, that is not. So we would say this data is not normally distributed. That doesn't mean we can't use it. It just means that we need to do a lot of different things with it or use other types of curves and more than we were going to do in this particular class. So all I want you to be able to do is kind of evaluate it. You can go to that appendix to help you. And you only have to do a homework problem for this. If I give it to you on the test, I might give you a graph and just determine if it's normally distributed. This might also, if you take a look at your textbook and just really look at 6.4 in your textbook, you'll have some examples. So look at 6.4 in your textbook and you can have some more examples of the normal curve. Okay? All right, so this is chapter 6.